G'day, welcome back to Mathematics for our final lesson in the Extension 1 HSC course. But before we get onto that, just a quick flashback from last video. We've got x being a discrete random variable with a binomial distribution. The mean is 1.2 and the variance is 0.72, so we want to find the values of n and p for number of trials and probability of success in each trial. If you watched the last video, you might want to pause and have a go yourself before I go through and spoil it for you in 3, 2, 1. All right, so starting off with our expected value being 1.2, the way we calculate the expected value or the mean for a binomial is we do n times p. Okay, so there's our first equation. The way we find the variance in a binomial distribution is we do np times 1 minus p. Okay, covered this in the last video. So these are the two simultaneous equations we are trying to solve to figure out what n and p are. Easiest way to do that is to substitute the first equation into the second, because wherever we see an np, we can replace that with a 1.2. So we can write this as 1.2 times 1 minus p equal to 0.72. Now we can just divide by 1.2 to get our value of 1 minus p, which is equal to 0.6. So if 1 take away p is 0.6, it must follow that p is equal to 0.4. And then we can chuck that into the equation up here where p is equal to 0.4. We can solve for n and we'll figure out that n is equal to 3. So we have a 40% chance of success and we have 3 trials. Okay, on to the last bit of content for the Extension 1 course, which is looking at normal approximations of binomial distributions and for sample variances. So pretty big lesson. Not sure how long this will go for, but it's definitely a case of the information in this lesson does seem a bit overwhelming. But once you see me run through some examples, you'll see it's actually not that scary. It's the same formulas and the same concepts repeated with some spicy HSC questions at the end to give you your fix. So let's dive right in. We're looking at an approximation of the normal distribution. So what you're going to see when you simulate a lot of trials in a binomial distribution, you're going to get a shape that's pretty similar to a bell curve, because a lot of the time your outcomes are going to be hanging around your expected outcome, which in this case would be 10. As you go further and further away from the expected middle, the number of outcomes or the probability is becoming less and less. And so the outcomes are sort of forming the shape of a bell curve. And we can use this fact to take some shortcuts with binomial distributions and approximate them as normal distributions to do some simpler calculations, okay? So the closer your success value is for p, the closer that is to 0.5, the more symmetric and bell curve like your distribution will become. Here's like a quick example. If you look at, this is called a Galton board or a quincunx, which is very confusing to say. Hopefully that doesn't get me demonetized. If you look at a bunch of binomially distributed outcomes, you will see them always forming a sort of normal-like distribution. The more trials you have, the more smooth that bell curve will become. So yeah, we're going to say as n approaches infinity, so as our sample size gets really large, our binomial distribution is going to be approximated to a normal distribution with a mean of mu and a standard deviation of sigma. So the way you calculate the mean is the expected value, which is np, and the way you find the standard deviation is you do the square root of the variance. So I'm going to go through all of this in a bunch of examples to give you an idea what I'm talking about. Here's our first one. We have a biased coin. Look how biased it is. It's got a 0.4%, it's got a 40% probability of flipping heads, which means a 60% chance of flipping tails. We're going to toss this 160 times because 160 is pretty close to infinity. And we're going to let x be the binomially distributed random variable representing the number of heads flipped. We're going to start off by finding our mean, which is our expected value, and our variance value for x. So using our formulas from last lesson, expected value is once again n times p. Our p is 40% and our n is 160. So quick calculation gets us an expected value or a mean of 64. So the center of our bell curve is going to be around 64. As our number of outcomes get higher or smaller than 64, they're going to become less frequent and we're going to see this sort of bell curve shape. So for our variance, we're going to do np 1 minus p once again. So we're going to do np is 64 and then 1 minus p is 1 minus 0.4, which gets us a value of 38.4. So for later on when we're going to need to find our standard deviation, all we need to do is the square root of our variance, which is going to be a really gross decimal, but these are all going to be approximations anyway, so we can do some rounding and not lose too much sleep. Okay, so noting now that our mean is 64 and our standard deviation is the square root of our variance, By letting the distribution be approximated as a normal distribution, find the z-score corresponding to 70 heads. Okay, so we're turning a regular score of 70 into a standardized score, which is called a z-score. So to do that, we're going to find the z-score using the z-score formula, which looks like this. Z-score is your original score. See how far away it is from the mean, and then divide that difference by your standard deviation. So we're going to do 70 minus the mean of 64 and divide that by our standard deviation up here in blue. This gives us a z-score of, rounded to 2 decimal places, equal to 0.97. Okay, so in a standard bell curve where the mean is 1 and the standard deviation is 1, the equivalent standardized score to a score of 70 in this distribution is going to be 0.97. So I will say, to access the content in this lesson, you had to have had studied the normal distribution in either more in an advanced maths course. If you have no idea what this is talking about, you're probably not ready for this lesson yet. Okay, so 0.97 now. Use the standard normal table to find the probability that less than 70 heads were flipped. Okay, this is becoming a pretty common part of Extension 1 mathematics exams. They get you to find some z-scores and then to find associated probabilities using a z-score table, which they provide in the exam. So I'll just run you through how to do that really quickly now with just a bit of really clever editing, because I'm really good at editing. All right, so here is the example from the 2023 HSC exam, which is the most recent at the time of recording. Here is the example of the standard normal table that they gave you. You've got a big table full of a bunch of z-scores from 0 all the way up to 3.29. And the numbers in this table are the probability that you are less than or equal to that z-score. So for the example we were looking at in the video, where our z-score is 0.97, if we look at 0.9 on the left and then go across to 0.7 up the top, 0.97 has a probability of 0.8340. So the probability that you are less than a z-score of 0.97 in a standard normal curve is the probability given in the table. All right, so this is all they give you. If you want to find the probability of being greater than a z-score, you just got to do 1 minus this answer to get you the rest of the bell curve up to 100%. They don't give you a sheet for the negatives. If you wanted to do a negative z-score, you would just need to use the fact that this bell curve is symmetric. So for example, if you wanted to find the probability of being less than a z-score of -1, that's the same thing as the probability of being greater than a z-score of +1. So you would go to 1, you would find the probability of being less than that, you would take 1 away from that to get the upper end of the tail, and that's the same thing as being less than -1. Okay, so they're probably only going to give you half the table. Got to use a bit of trickery, and just keep in mind this thing is very symmetric, and that makes it a bit more doable. Okay, sweet. Back to the slideshow. Okay, now we've covered that. Let's continue on. So this is the row we're looking at in our z-score table. 0.97 was just here, which is 83.4%. So that is the probability that we are less than a z-score of 0.97. So that's going to be roughly equivalent to being less than 72 correct coin flips, or flipping heads 72 times. Okay, so there is our probability, 83.4% or 0.8340. Okay, on to part D. Find the probability that at least 72 heads were flipped. So this is going to be a similar process again. We're going to have to turn 72 into a z-score, and then the table we're working with gives us the probability of being less than that z-score. So we'll just have to do 1 minus to get the probability of being greater than. So turning 72 into a z-score by doing 72 minus the mean divided by the standard deviation once again. This gives us a slightly higher z-score of 1.29. Okay, now if we flip back to our table, I'm not going to do it on screen each time because I'm lazy, and editing is very tricky for me because I'm not very good at stuff. But the table tells you that the probability of being less than 1.29 is equal to 90.15%. But because we want to be greater than that, we'll just do the complement, which is 1 minus this. So less than 72 or less than a z-score of 1.29 is 90.15%. So being greater than that would be 9.85% if I did my maths correctly. I think I did. Okay, beautiful. On to the next one. This is an HSC question. Whoa, slow down. This is an HSC question from 2020. It's covering bands 2 to 4, but all over pretty simple concepts once you are aware of how to approximate these with z-scores. We've got a bias coin. Again, more bias coins everywhere. We have a probability of heads of 3/5, which was the same as last time. Anyway, no, it's not. That was 40%. This is 60%. Ignore me. The coin is tossed 100 times, so we are doing an n of 100. X is the random variable of number of heads obtained, and this will have a binomial distribution. And we're going to approximate this as a normal distribution later on. Okay, first part for a quick and easy mark is find the expected value EX. So noting that our probability of success is 3/5 and our n is 100. If you get this wrong, you're having a bad day, because E of X is just n times P. So it's 3/5 times 100, which gets you an expected number of heads out of 100 trials being 60. So 60 is the average. The further you get away from 60, the less likely that outcome is going to become. Okay, for part 2, by finding the variance, show the standard deviation is approximately 5. So using our variance formula once again of NP 1 minus P. So we have 60 for NP, and we have 1 minus 3/5 for 1 minus P. This gives us a value of 24, which is pretty close to 25. So when we do the square root of our variance to get our standard deviation, it's going to be like 4.9, which we're going to say, that's close enough to 5. So for the rest of this question, we're allowed to use that 5 is approximately our standard deviation for the second mark. Okay, for the third mark, which is the only kind of hard part, is by using a normal approximation, find the approximate probability that X is between 55 and 65. Okay, notice that this question makes no mention of a data sheet or of a normal table, so we shouldn't need one. The reason we don't need one here is because we're looking at 55 and 65, and 60 is the average and 5 is the standard deviation. So the scores 55 and 65 are just one standard deviation down and up from the mean. So when your step size or your Z-score is a nice and whole number, you don't need to use the sheet that they provide you. You can use the bell curve on your reference sheet. So for the probability of number of heads being between 55 and 65, this is the same thing as a Z-score being between -1 and 1. And if we look at the magic bell curve on our reference sheet, it says that between -1 and 1, pardon me, this is approximately 68% of your data set. So we can say that the approximate probability that we're getting heads between 55 and 65 times is from here to here, which is approximately 68%. Okay, so keep in mind, slow down. Keep in mind, when your Z-scores are nice whole numbers, use the bell curve rather than the table. But they haven't asked a question like this in the last 3 years, so I don't know whether these are going to be regular occurrences in HSC, because this technically isn't specified in the syllabus, but you never know what NASA will do. They are off their heads. All right, on to the second part of the lesson, which is all about sample proportions. These are definitely explicitly mentioned in the syllabus, and there's been a question on this stuff every year for the last 4 years. So you can definitely expect to see this in your HSC this year. I bet my life on it. Well, I bet your life at least. All right, sample proportion. This kind of makes more sense to me if I talk about it with real numbers and real examples. So apologies if this is a bit long-winded. Like I said, the explanation, the information is dense, but the examples you'll see are all very similar, very straightforward. Okay, 15 students in a class, and let's say 4 of them are smarter than the teacher. In my class, it's a much higher number. The sample proportion of the random variable smarter than the teacher is given by this notation here with a P with a hat above it. This doesn't mean a probability, it means a sample proportion, which is kind of like a probability based on real numbers. So 15 in the class, 4 are smarter, so the sample proportion of people smarter than me is 4 out of 15. This is the same thing as if I picked a random student in my class, the probability they are smarter than me is 4 out of 15 based on our proportions in our sample. Okay, so if we take all of our outcomes from our binomial trials, which could be number of students smarter than me from 0 up to 15, if we divide all those by 15, we turn those outcomes into sample proportions. Okay, so when we're reading sample proportions, we're thinking binomial outcomes as fractions. Okay, binomial outcomes as fractions is the simplest way of thinking about it in my mind. Okay, more info, bloody plus. So because the sample proportion is so closely linked to a binomial distribution, we can also approximate sample proportions using a normal distribution in the same way that we did with the binomial outcomes. So similar approach with some different values, okay? The probability of a sample proportion being equal to some sort of fraction is the same question as asking what's the probability of getting that many successes in your binomial trial. So bloody blah, it's all the same stuff. Translation of this is that the probability of our sample proportion was 4/15 from earlier. And this is the same thing as saying, hey, what's the probability we have 4 success trials of being smarter than me out of 15 trials. Anyway, sorry if I'm over-explaining this, but I needed to over-explain this to me when I taught this for the first time, just to sort of make sense of things. So apologies if I'm rambling. Okay, just like binomial distribution, the sample proportion approximates normal, like I said, assuming that your n is a decent size. Okay, so it's only going to be pretty bell curve shaped if you have a large sample size, otherwise it'll be all janky. Okay, so for our mean and variance, importantly, these calculations are not on the reference sheet. So the mean and the variance of the binomial distribution are on there. For the sample proportion, they aren't. In some of the HSC questions recently, they've been giving you these formulas. Sometimes they don't. So this is definitely a couple of formulas that you definitely want to memorize. Otherwise, you're not going to be able to access some of the HSC questions. So for our expected value of the sample proportion, the expected value is just P, which is the probability of success. Which makes sense, because if you told me that there were, 4 students in my class smarter than me out of 15, that means that if I picked a bunch of kids, I would expect 4 out of 15 of them to be smarter than me. Okay, so the expected value of your sample proportion is just the probability of success. For your variance, so before we were just doing NP divided by N, and that got us P. For our variance calculation, when you calculate variance, as you may have seen in the earlier lesson, it involves squaring your outcomes. So the n is actually going to become squared. And so we have our variance from before, which is np, 1 minus p. And instead of dividing by n, we're dividing by n squared, because that's how the variance formula works. It's squared stuff. Okay, so these two n's are going to cancel off, giving us p, 1 minus p divided by n as the formula for the variance of our sample proportion. And of course, don't forget, if you want to find the standard deviation, as per always, you've got to take the square root of your variance. Okay, so blue and red absolutely need to be memorized, and you should already hopefully know green. Okay, time to dive in and do a bunch of maths until your brain bleeds and this stuff makes sense. All right, a recent census showed 15% of adults worked from home. We're doing a survey of 120 adults. P hat is going to be the binomially distributed sample proportion of people who work from home. Question A, find the mean and standard deviation of the sample proportion. So straight away, easy marks, because we're just using our formulas for mean and standard deviation of P hat. So as soon as you see P hat, you think these formulas, okay? Link them in your brain and it's bulk marks for you. So starting off, we're gonna say that our percent of success for working from home is 15%, because it says 15% of people work from home. Our sample size is 120. So starting off with our expected value, which is just P, which is just 15%, or you can write 0.15 if you prefer. Rise a fraction, I don't care, do whatever you want. For the variance, we're doing, there you go, either one's fine. You're so sweet. For the variance, we're doing P, 1 minus P divided by N. So we've got 15% times 85% divided by sample size of 120. Okay, this works out to be a disgusting decimal of 0.0010625. Some of the questions today are going to work out to have nice decimals. This first one, for some reason, is not one of them. Okay, so that's easy. That's the first part done. That's mean and variance of the sample proportion working from home. Part 2, find the probability that, at most, 24 people from the survey work from home. Okay, so to do this, we are once again going to use a normal approximation of our sample using the same mumbo jumbo as before. So starting off with, what is the sample proportion of 24? So remember, for all these questions, for the second half of this lesson, we're not working with outcomes, we're working with proportions. So first thing we're going to do is take 24 and we're going to divide it by 120 to turn it into a proportion. So we're trying to find the probability that less than 20% of people are working from home. So the way we're going to do that is we're going to turn 20% into a Z-score. To do that, we're going to need our standard deviation. So standard deviation is the square root of our variance from before. Works out to be approximately 0.0326. So now we can say that P hat is approximately a normal distribution with a mean of 15% from before and a standard deviation of 0.0326 roughly. I know that's not a perfect approximation, but we're doing a lot of guesswork today. Okay, so turning our 20% into a Z-score using our Z-score formula from before. We do 20%, take away 15%, because that's the mean. Divide that by the standard deviation, which is 0.0326. Gets us a Z-score of approximately 1.53. We're always going to round these to 2 decimal places, because the tables that we're working with only use 2 decimal place accuracy. Okay, this is the point where we grab our standard normal sheet from before, like I showed you on the screen. You look up a Z-score of 1.53. And hopefully what you can see is that it's going to say 9370 after decimal point. This means that the probability of having a z-score less than or equal to 1.53 is 93.7%. So that's equivalent to the proportion of our working from home being 20% or less. Okay, so get your number, turn it into a fraction or a percentage or a decimal, whatever you prefer. Turn it into a z-score, use your z-score table to obtain your answer. Those are the steps that we're running through today, okay? Fractions, formulas, z-scores, tables, all the good stuff. Once you do it 5 times, you'll be able to do it for the rest of your life. Okay, for part C, find the probability that at least 15 people from the survey worked from home. We want to turn 15 out of 120 into a z-score and then find the probability of being greater than that. But it's already looking like this video is going to be 100 hours long, so I'm going to say you have a crack at that yourself and let me know in the comments what your probability is, and if you're right, I will send you a like straight from me to you. You've earned it. On to example 2. 10% of all professional Rubik's Cubers are over the age of 25. This was my backup plan if math teaching didn't work out. Sadly, it did work out, and now I'm talking to my computer every Monday night to make videos for like 10 people. Anyway, 10% of Rubik's Cubers over 25. A random survey of 100 Rubik's Cubers was carried out to determine how many were over the age of 25. Assuming that this is normally distributed, calculate the expected mean and standard deviation of the group. This is great news. Whenever we see a question like this, as long as we know the formulas, this is free marks for us. So straight away, we're recognizing that it's a sample proportion question. So first of all, we're going to say, all right, our probability or our probability of success is 10%, and our number of trials, our sample size is 100. So running through our formulas, our expected value for the sample portion is we expect to get a proportion of 10% because that's just based on the stats. Okay, so expected value is 0.1. For our variance, we're going to do 0.1 times 0.9 divided by the sample size of 100, which gets us a value of 0.0009. Which is really good because when you do the square root of this to get the standard deviation, this is actually a nice number. The square root of 0.00009 is 0.03. So now we have our bell curve ready to go. We have our mean of 0.1 and we have our standard deviation of 0.03. Okay, so that's part A done. On to part B now, where we're actually going to use these values. Part B is using a z-score probability table, estimate the probability that at least 15 cubers surveyed will be over the age of 25. Okay, so to do this, we need to turn some stuff into z-scores. So we want 15 cubers out of the 100 that we're surveying to be over the age of 25 years. So we're trying to find the probability that our sample proportion is at least 15 out of 100. So once again, first thing we've got to say is bloody blah. We've got a normal distribution with a mean and a standard deviation. Turning our 15 into a proportion, we're going to say we don't want 15, we want 15 out of 100, which was our sample size. So the figure we're working with is 0.15. Okay, now what we're going to do is turn 15% into a z-score so we can use our z-score probability table and figure out our answer. So using our z-score formula for like the 4th time today, and we're going to use it a few more times, 15% minus 10% divided by standard deviation gives us a z-score of approximately 1.67. So now we bust out the table. In the HSC, it'll be at the back of the exam. If you're working on this right now, you might have one right next to you. Look up the z-score of 1.67. And because we want to be greater than, we want at least 15 cubers, we're going to look up 1.67 and we're going to do 1 minus that value because the thing on the page gives you the area up to that point. We want the area beyond that point. So hopefully from the table, 1.67, you can read it and it says 0.9525. If we do the rest of the bell curve by doing 1 minus this, we get our approximation of 4.75% of our survey cubers being 15 or more over the age of 25. So there's our answer right there, 4.75%, done and dusted. Okay, we've got a few more to get through. Let's go on to example 3. After counting votes, oh God, McGrathmatics has got political again. Hopefully this gets me cancelled. We've got 40% of people voting for Donald Trump after 600, you know what? Yeah, let's go through this. Okay, a sample of 600 voting cards taken and inspected. Assuming we have a sample portion, that's the 2 keywords, write down your formulas. Approximately normally distributed, what is the probability that less than 216 cards indicated votes for Donald Trump? Okay, so we're running through all the same steps again. We are getting our formulas, getting our mean, getting our variance, getting our standard deviation, getting our z-score, and getting our table. So it's a lot of steps, but they're the same thing every time. So hopefully you're starting to get the hang of this now. First of all, we can see our P, our probability of success in our sample is 40%. 40% of people voting for Trump. Is that a success? Hard to say. Okay, our N for number of voting cards is 600. So starting off with our expected value, our expected mean of the sample proportion, which is 40%. If we picked a bunch of cards, we would expect 40% indicate Trump voters. Okay, and now for our variance, we're doing 40% times 60%, dividing this by our sample size of 600 voting cards. So we have 0.4 times 0.6 divided by 600, which is 0.0004, which is another well-designed question. Thank you, SmartMaths, for this one. Because the square root of 0.0004 is equal to exactly 2%, 0.02. So now we have our bell curve ready. We have our center point of 0.4 as our mean, and we have our standard deviation of 0.02. Now the number we're interested in is we want to find the probability of having less than 216 cards indicate votes for Trump. So what would that be as a proportion? It would be 216 out of 600. So let's turn that into a fraction. We have our normal distribution ready to go. Why am I so bad at saying distribution? Distribution. Turning 216 into a fraction, 216 out of 600 is equal to 36%. All right, now let's figure out what our z-score is. So using our z-score formula, 36%, take away our mean of 40% divided by 0.02. This gives us a z-score of exactly -2. Hey, what did I say to do when your z-score is a nice whole number? You don't need the table, all you need is the reference sheet and a pretty little bell curve. So now we're going to do some maths. We want to find the probability of being less than 216, which is a z-score of -2. So putting that over here, we are trying to find, am I going to put on the picture? Am I going to put on the picture? I'm not, okay. That was meant to be a picture here. We're trying to find the area of less than -2, which is down here. Okay, so we know that between -2 and +2 from the info, it's going to be 95%. That means beyond 2 and beyond -2 must be the rest of the bell curve, which is 5%. So if there's 95% in here and there's 5% out here, each of these tails must be 2.5%. So we have 2.5% being less than -2, and we have 2.5% being greater than 2. So that's why our answer is simply that the probability of a z-score of less than -2 is 2.5%. So there's our answer. That's the probability that less than 216 cards indicated votes for Trump out of 600. Okay, please keep any politics out of the comment section because I can't be bothered. Okay, on to example 4, which is a little bit different to the one so far, but it's pretty similar to a recent HSC question. We have manufacturers, this is a long video, we have a probability of our parachutes being defective of 3%, which I think conservatively is too high. I don't want to go skydiving if there's a 3% chance I'm going to die, but I don't want to go skydiving anyway, so why do I care? Okay, p hat is the random variable representing the sample proportion of parachutes for samples of size n drawn from production. So this one's interesting because we don't know what the sample size is. We want to find what the smallest value of n is such that our standard deviation of p hat is less than a 50th. So we want to make a sample size big enough to make our standard deviation less than a 50th. Okay, so we see sample proportions and we see means and we see standard deviations and we think, oh, let's just write down some formulas and have some fun. So we have our p probability being 0.03. Our n is unknown, but we can figure that out later. Okay, so starting off with our variance, because we want to find our standard deviation for this question. Variance formula once again is p, 1 minus p divided by n. We don't know what n is, but we know what p is. So the top is 3% times 97% divided by n. Okay, if you simplify this fraction a little bit to get the decimals out of the way, it works out to be 291 out of 10,000 n. Now this is our variance. So to find our standard deviation, we're gonna have to do the square root of this to get this as our standard deviation, okay? Standard deviation, square root of variance. Now we wanna find a value of n that makes our standard deviation have a value of less than 1/50th. So this is the equation we have created for us, and we're gonna go ahead and solve it. This is not too bad because we know that the value of n is gonna be positive, so it makes the algebra a bit less restrictive. Let's start off by squaring both sides to get rid of that square roots. When you square a 50th, you get 1 squared over 50 squared, which is 2500. And now we can just do some cross multiplication. We can times the 2,500 across to the left, and we can times the 10,000 n across to the right to look like this. Okay, now 291 times 2,500 is equal to 727,500. While I'm here, I'm just going to swap the sides over and put the larger side on the left. Now we can just divide by 10,000 and we get an expression for n. N needs to be greater than 72.75. And the question wants us to find the smallest whole number value of n. So because we're greater than 72.75, we're going to have to say 73 is the minimum whole number we need with this value of p to give us a standard deviation of less than a 50th to apparently make them safe for mass production. And only 3% deaths, that's pretty good. It's better than some schools. Okay, finishing off with some HSC questions. This one's from 2023, very recent. It's a band 4. You see band 4 and you think scary. This one's actually very straightforward, but let's just dive in. We have 30% of Australians in a recent census that are born overseas. A sample of 900 randomly selected Australians are surveyed. P hat, we see P hat and we think formulas. I know the formulas. P1 minus P over N, I know it. Okay, a normal distribution is used to approximate the probability of the sample proportion being less than 0.31. Show that the variance of the random variable, is 7 over 30,000. So this is Nessa gifting you 2 marks just for doing a bit of study and memorizing some formulas. So let's dive in and get them for free. Okay, should we start off with our expected value? I can't remember if I'm going to, but we know that our P from the question, we have probability being 30% and our sample size is 900. That's obvious to anyone who is literate. Now we can find our expected value for our sample proportion, which is 30%, of course. Using our formula to find our variance, we have P1 minus P over N for like the 12th time today. So we have 30% times 70% divided by the sample of 900. And we're trying to show that this is 7 over 30,000. And would you believe that into a calculator is 7 out of 30,000? That's like the easiest 2 marks I've ever seen in the HSC. Now we can do part 2, which is use the standard normal distribution on the information page 16 to approximate the sample proportion being less than or equal to 31%, correct to 2 decimal places. So we've done a bunch of these today. Now we're doing it for real in the HSC. All we're going to do to use our standard normal table is to turn 0.31 as a sample proportion into a z-score. So let's use our z-score formula. Before we do that, we're just going to make a note that our standard deviation is once again the square root of our variance. And now we can dive into our z-score formula, doing our original score, which is 0.31, subtracting the mean of 0.3, which is p, and dividing by the standard deviation. This calculation gives us a z-score of approximately equal to 0.65. So now is the time where you grab your standard normal table, you look up the z-score of 0.65, and it'll tell you the probability of being less than a z-score of 0.65. Okay, hopefully you've done that, and hopefully you're seeing a value of 0.74. This is rounded to 2 decimal places, by the way. So there's the answer. The probability of being a z-score less than 0.65, which is equivalent to a sample proportion of 0.31, it's equal to 0.74. That's 4 marks in like 6 lines of working. This is easy stuff, like I said. Band 4, as if. This is like band 1 for us now. From the standard normal table. Okay, and now to finish off, thank Christ, I think I'm getting delirious. This is like a 600-hour video. This is a band 5. This one's actually pretty challenging from 2021. Let's dive in for 3 marks. Certain factory, proportion of faulty items is 3 out of 500. That straight away gives you a value of P, and that is acceptable, okay, if you say so. To confirm the machine is working to this standard, a sample size of n is taken and the p hat is calculated. So we see p hat and we think formulas. This is a nicer question because they gave you the formulas. You don't have to memorize them, but that's usually the easy part. So there's your formulas. The production in this machine will shut down if the sample proportion is greater than 4 out of 500. The sample size is to be chosen, so the chance of shutting the machine down is less than 2.5%. We've seen 2.5% already today. Well done if you recognize it. Find the approximate sample size required, giving your answer to the nearest 1,000. Okay, so this is a merging of a couple of questions we've already done today, which is why you could say that this lesson is like expertly made. But anyway, we're trying to find a value of n, and we don't know it. Okay, so what do we know? We know our p, we know our n, and we've got our formulas. So why don't we dive in and start doing some formula calculation. Also make note of the fact that we're trying to find the value, we're trying to find a sample size that makes the probability of p hat being greater than 4 out of 500 being less than 2.5%. All right, so starting off with our p, which is 3 out of 500, n is unknown. Now, thinking about our bell curve from before, 2.5%, if you remember, was the probability of having a z-score of less than -2, as well as the probability of a z-score being greater than 2, which is up here, okay? Because there's 95% within -2 and 2, so there's 5% outside of -2 and 2, which is 2.5% down here and 2.5% up here. This whole question kind of relies on you sort of spotting that and saying, all right, cool, so I want to have this number right here where the probability of being greater than this is 2.5%. So putting this all together, we're really just trying to find the values that make 4 out of 500 give us a z-score of 2. If we can find the n that makes that happen, we've got 3 marks in a band 5 question. So there's our target, let's go for it. Once again, we're trying to find the value of n that makes 4 out of 500 a z-score of +2. That's what I said. Okay, so let's start off by using our z-score formula. So for our x, the number that we're working with is 4 out of 500. The mu is the mean, which is of course p, which is 3 out of 500. N is unknown, we don't need that. The standard deviation we can calculate. Oh, no we can't. We're gonna find an expression for the standard deviation and then use that to figure out what our n is. What we do know is the left-hand side, which is our z-score. We want that to be 2 to be on this point right here. Okay, so solving this equation, we get multiply the sigma across there, funny word, we get two standard deviations is equal to 4 500ths, take away 3 500ths, which is 1 500th. Okay, divide this by 2, and we've figured out that for this equation to work, the standard deviation needs to be 1 over 1000. Okay, this is the hard work done so far. Now all we need to say is, all right, we want the standard deviation to be 1,000th. What's the value of n that can make that happen? Well, to figure this out, I'm going to need to use my variance formula and then square root it to get my standard deviation. So let's do that. Sigma needs to be 1,000th. Okay, variance formula, as they told us in the question, it's the square of the standard deviation is variance, which is p, 1 minus p over n. We don't know what n is, but we know that p is 3 500ths, which is 0.006, which means that 1 minus p is 0.994. Now, the left-hand side, which is our squared standard deviation, we already figured out the standard deviation needs to be 1,000th. So this is the equation that we are now attempting to solve for n. Okay, we're going to start off by flipping both sides to make the algebra a bit more friendly. So the left-hand side becomes 1,000 squared divided by 1 squared. The right-hand side is our multiplied decimals on the bottom and on the top. Okay, now that we've made that flip, it's nice and easy. We can just multiply this product across the left-hand side with the 1,000 squared and say n is 1,000 squared times bloody blah. This calculation is approximately equal to, in fact, it's exactly equal to 5964. So we need our sample size to be 5964. The question asks us to give our answer to the nearest 1,000. So the nearest 1,000, we're going to say, very good. If our sample size is 6,000, then this gives us a standard deviation of 1,000th, which makes 4 out of 500 have a z-score of 2, which means the probability of being above this is only 2.5%, and there's the question done. So that's how hard these questions can get in the HSC, but it just relies on a lot of confidence with the formulas, a lot of confidence with the bell curve, and a lot of confidence with just the concept that's happening. But yeah, the band 5, band 6 questions, HSC are never going to be friendly, but that's how we tackle one of them. Okay, I'm very tired, but that is the end of the Extension 1 course. So hopefully that made you a little bit more confident with dealing with sample portions and some HSC questions. If there's any more content from Extension 1 you feel you could use before the HSC exam, let me know, because I'm going to be making a few revision videos over the next month. So tell me what you want to see, and if I have time, I will do my best to make it, but I'll also be putting out some Extension 2 videos to revise. So stay tuned for that. If you made it to the end of that, well done. You're very brave and hopefully very smart. And thanks for your support. Thanks for watching. And I hope you're learning. I'll see you guys in the next lesson. Bye for now.